Okay, so in today's video, we're going to be finding the first derivatives and second derivatives of a variety of different problems, and we're going to be looking to find the critical points of these different functions that we'll take a look at. So the first question is, we have two different functions. So f of x is equal to x to the power of 5 minus 5x to the power of 4 plus 17. And then the second function, g of x, is 10x squared over x minus 7. Okay, so in this video, I'm literally just doing these questions for the very first time, so I've not actually seen them. So what you're going to be seeing is me just literally working through it and trying to solve them. So at the same time, you should try and solve them, and basically we'll just be working through them together. So it's asking us to find the derivatives of f of x and g of x. So the first derivative of f of x is just going to be, it's going to be 5x squared. So here we'll just put down here. So the first derivative of f of x is just going to be 5x to the 4, not 5x squared, sorry. So we multiply by the power, and then we decrease the power by 1, minus 20x to the power of 3, and then that's going to be the first derivative of f of x. Now g of x, we're going to be having to apply some of the rules that we had before. So what we essentially have here is 10x squared times x minus 7 to the negative 1. Now, actually, because we have this function in a fraction, we can use the quotient rule. So I'm actually going to look over my notes to see the quotient rule formula. Okay, so I've got the quotient rule formula. So I'm going to bring g of x down here. So it's going to be 10x squared over x minus 7. And quotient rule basically means that we essentially separate the one function into two different functions, basically. So if we let this here be h of x, and then the denominator we let it be, I don't know, let's say a of x, then the first derivative is going to be the first derivative of our numerator multiplied by our denominator, subtract our numerator multiplied by the first derivative of our denominator, all over the denominator squared. Right, so a of x squared. Okay, so first derivative of h of x, this is very messy, right? This is just literally me doing this in my mind. So this is going to be then 20x, and then the first derivative of a of x is just going to be 1. Okay, so then g of x, the first derivative of g of x is going to be first derivative of h of x, so 20x times ax. So it's going to be 20x times x minus 7 minus h of x, which is 10x squared, times the first derivative of a of x, so times 1, all over ax squared. Okay, so it's just going to be x minus 7 squared. Okay, so now we can just we can expand this out. We can simplify it down, actually. So then it's going to be g of x is equal to 20x squared minus 140x minus 10x squared over x minus 7 squared. This is then going to be 10x squared minus 140x over x minus 7 squared. So that's going to be the first derivative of g of x. So let's go ahead and plug these answers in. So first derivative of f of x we said was 5x to the power of 4. So let's see here. So 5x to the power of 4 minus 20x to the power of 3. Let's see if that's correct. And then g of x, we said was 10x squared minus 140x. Minus 140x all over x minus 7 squared. Okay, let's see if these two answers are correct. Awesome. Okay, so those two are correct. Okay, now we are on to question 2. So it's saying let f of x, 2, so I'll write here 1 and 2. F of x is equal to, oh, actually they're giving us the same thing. G of x is 10x squared. Okay, now find the x values of the critical points of f of x and g of x. Okay, so the x values. So critical values essentially are the turning points or the points of inflection on a curve. So this here would be a local maximum, and that's a critical point. Down here is a local minimum, and that is a critical point as well. If a curve, for example, does something like this, where it's looking like it's going to be a local maximum, but then it turns and goes and it's going to be a local minimum, right? This here is a point of inflection, okay? Because if we were looking at it here, for example, this right now is looking like it's going to be a local maximum, okay? We can see that the gradient of the tangent to the curve, as we're increasing along the x-axis, it's becoming less and less. The gradient's becoming less and less. So it's giving us signs that it's going to be a local maximum. But then, in reality, it then starts to do this, and it starts to increase. So it was decreasing, the gradient to the tangent of the curve was decreasing. Now it's starting to increase. So that means that the point between where that changes, that is the point of inflection. So that is a critical point. So we have 3 different types of critical points. So the question here is asking us, find the x values of the critical points of f of x and g of x. So let's first look here at the first derivative of f of x. We have 5x to the 4 minus 20x cubed. Now, critical points are where the gradient, right, you can see here, where it's a turning point, turning point, turning point. All of these here, the tangent to that respective point is a horizontal line. And at that point, right, the gradient is 0 because we aren't rising anything. We're going across, but we aren't rising anything. So the gradient is 0. Now, our first derivative gives us the gradient of a curve at a certain point. So if we set this here to 0, that is how we are going to find the x coordinate of the curve when it is equal, when the gradient of the tangent to that point is equal to 0. So what we can do here instantly, we're going to see x is equal to 0 is one answer, right? If we put 0 in here, then the answer in the equation will be satisfied, right? It will be correct. If x is equal to 0, 0 is equal to 0. Okay, so that's our very first answer. So x is equal to 0, that's going to be 1. Now, to find the next answers, what I'm very simply going to do is I'm just going to divide the entire equation, equation by x cubed. Okay, and so that's going to leave me with 5x minus 20 is equal to 0, 5x is equal to 20, 5x is equal to 4. So it's going to be my second answer. So if I look at this here, if we substitute that in, so 5 times 4 to the power of 4 minus 20 times 4 to the power of 3 equals 0. Okay, so that is another answer. So then I'm going to enter that in 4. Now, I'm pretty sure that's going to be all of the answers. We could do 5x cubed x minus 4x, or x minus 4 is equal to 0. Right, that's basically just what we did there. We factored out the x cubed and then the 5 as well. We factored it out here. Okay, so those are going to be the two answers for that. For f of x, the critical points, those are going to be the x values of the critical points. And now g of x, so we're looking here, so it's going to be 10x squared minus 140x over x minus 7 squared. Okay, first things first, if any fraction has a denominator that's 0, then it's undefined. So that means that x cannot be, right, 7 is a value for which our function is undefined. Okay, so typically, if you have the first derivative and you're getting undefined, that means that the gradient of the tangent to the curve at that respective point is going to be a straight line. Now, if that does happen, then yes, it's a straight line. However, in these sorts of cases when it's undefined, you then have to substitute that x value into the original equation to make sure that it's actually a point on the curve. And if we substitute 7 into our original g of x function, then we're going to get undefined again. And so that means that 7 actually isn't a point on this function. Okay, so instantly we know 7 is not going to be a value on this function. Now we're going to then look here. Okay, how can we make the numerator 0, right? If we have 0 over 8, that's just 0, right? 0 over any number is just going to be 0, so that is going to be working. So I'm going to then bring this down here. So 10x squared minus 140x is equal to 0. And then again, we have x is equal to 0. If x is equal to 0, this numerator is going to be 0. Then I'm going to divide both sides by 10x. So what am I going to get? X minus 14 is equal to 0. X is equal to 14. Now if I substitute that in, 10 times 14 squared minus 114 minus 140 times 14, is equal to 0. Okay, so that works. So these here are going to be our two answers, 0 and 14. Now let's quickly check these. Awesome, and those two are correct, right? So it was very important here to identify basically what values can this function not be, right? What critical values of x don't work for that function there. Now let's look at the next question. Okay, so we have the function h of x is equal to 3x to the power of 4 minus 12x to the power of 3. And the question's asking us to find the x and y intercepts of h of x. Okay, so what is that going to mean? So we've got our function, whatever our function is going to be. We're trying to find the y and the x-intercept. So it's good just to know straight off the bat what we're actually going to be doing. So first things first then is we're going to, okay, so we're finding the x and y intercepts of h of x. So very simply, to find the y-intercept, all we just do is we set x is equal to 0, right? Because at y, the y-intercept, x is 0. So that then means that the y-intercept is going to be 0, 0, right? That's going to be the coordinate. And then the x-intercepts. So x-intercepts occur where y is 0, okay? So the x-intercepts will occur somewhere along the x-axis, and our vertical displacement, right, the distance up and down the y-axis is just going to be 0. On the x-axis, right, we are So how do I explain this better? So we're here, we're on the x-axis, and because we're on the x-axis, we're at y is equal to 0. We're not below the y-axis, we're not below the x-axis, and we're not above the x-axis. We're on the x-axis, therefore y is equal to 0. So we can just set this function here to equal to 0 in order to find the x-intercepts. So straight off, we know 0 is going to satisfy this equation. So if x is equal to 0, then the equation will be satisfied. So 0 is equal to 0. Then if we just divide everything by 3x cubed, what that's going to leave us with is x minus 4 is equal to 0, x is equal to 4. So that's going to be our second. Now we also have to find the y coordinates. Oh, and actually, I just answered it before. At the x-intercepts, the y coordinate is 0. So we're going to have the coordinate 0, 0, and then 4, 0. So let's see, because we already did enter 0, 0. Let's see. Okay, so that's correct. So we had that duplicate. Well, actually, yeah, where intercepts, if it's at 0, 0, then it's intercepting both the y and the x. So it makes sense to be accepted. Okay, now they're asking us to set up a table of signs for the first derivative. Find the intervals where the function h of x is increasing or decreasing. Okay, so we have basically two critical points, 0, 0 and 4, 0. So here. Now let's firstly find the first derivative of h of x. This is going to be 12x cubed minus 36x squared. So at x is equal to 0, we want to basically see what's going to be happening at x is equal to 0. So what is the first derivative of f of x going to be? Okay, so we obviously know from one of the previous examples, the first derivative finds the tangent of the straight line to a point on a curve. So let's say we have this is h of x. Let's pretend it's h of x. And we want to find the gradient of the tangent to a point on that curve. So we'd then find the first derivative and then substitute that respective x coordinate in order to find the gradient at that point. So, and we know, right, if the first derivative is positive, it means that the gradient is increasing. If the curve is increasing. If the first derivative is going to be negative, that means that the curve is decreasing. So here we have 0, 0. This is our very first critical point. So if I go ahead and I get let's then put a value like -1, and then let's put 1 here. So you have -1 and 1. So if I go ahead and substitute 1, so 12 times 1 to the power of 3 minus 36 times 1 squared, that's going to be -24. Now we know that at 0 is just 0. Now if we substitute, oh, that was supposed to be, oops, okay, so my bad, that's -24 there. And then here is going to be the -1. So that's my mistake there. -1. That's going to be -48. Okay, so it's decreasing. Then the gradient is 0, and then it's decreasing again. Our next critical point is then where x is equal to 4. So let's substitute 4, and then we'll do a value after 4, which is 5. So let's go ahead and substitute 4 here to see what the behavior is. It should be, well, this critical value. Actually, no. Okay, so that's 192. Wait, so what is this? Okay, so this means here now it's increasing. And then if we enter in 5, the first derivative is that, and that's also increasing. That's still increasing, okay? So what we're basically seeing then is that we had this downward curve, then it went like that, the gradient was 0, then it continued going down, and then so here we figured out the critical points. Wait a second. So here we found the x, oops, okay, so this is incorrect actually. So here we found our intercepts on the y and the x axis. Oh, okay, so that was actually slightly wrong. Okay, sorry. So the idea was fine, but I was using incorrect numbers. So here we want to set this to equal to 0. So 12x cubed minus 36x squared is equal to 0, right? We want to see where is the gradient to the tangent of the point on this curve equal to 0. Okay, where is it stationary? And instantly we know it's going to be at x is equal to 0, so that was correct there. And where else is it going to be? Well, if we divide both by the entire equation by 12x squared, we're going to get x minus 3 is equal to 0, x is equal to 3. So at these 2 points, this is where the curve is going to, these are the critical points of the curve. So this is where the gradient of the curve is going to be stationary. So here, as I wrote it, it was actually correct. So -1, 0, 1. So we had -48, 0. That's the first derivative of f of x. -24. Then we were looking at 3, and we know it's going to be 0, right? If we plug it in here, oops, I can't actually undo that. 3 cubed minus 36 times 3 squared, 0. Okay, so the first derivative of f of x at x is equal to 3 is 0. Now let's get a number that's bigger than 3. Let's say 4. And as we saw here, it was 192. Okay, so here the curve is going down. Then it's stationary. Then it's going down again. Then it's going to be stationary. And then it's going up. Okay, so if we do a graphical illustration of this information, we see it's going down. Then it's stationary. Then it's down. Then it's stationary. And then it's up. Okay? So let's say this is 4, 3, 1, 0, -1. Okay? That is the sort of shape of the curve. So the question is asking us the intervals where the function is increasing. So the function is going to be increasing from where x is equal to 3 up to infinity. Essentially, that's what we're saying. And it's going to be decreasing from -infinity down to 3, right? But not including 3, okay? So we have these important values, right? These are our critical values. 3, and that's essentially where the curve, where the function stops decreasing and it becomes increasing. So we want to find that y coordinate. So if we substitute that into that x value of 3 into our initial function, so 3 times 3 to the power of 4 minus 12 times 3 cubed, we're going to get negative 81. So the critical point here is 3 and negative 81. So where the function is increasing. Now, we know that in intervals, circular bracket means doesn't include. Square brackets means it includes the respective value. So interval where the function is increasing is going to be from not including 3 all the way up to infinity. So let's see here. So all the way up to infinity. Oops. Okay, so 3 all the way up to infinity. That's going to be for our function increasing. Now, here, we actually also need to figure out, okay, so this is the other critical point, because here the function isn't decreasing, it's stationary. So what's the y coordinate going to be? If we substitute x is equal to 0, we get y is equal to 0. So 0, 0. That means that the intervals where the function is decreasing, that's going to be negative infinity. So negative infinity. And for infinity, we always have the circular brackets, comma, till 0, again, circular brackets, and then we're going to have the second interval. Let's see if I can find the symbol here. Okay, the second interval is then going to be 0 all the way to x is equal to 3, again, not including 3. So it's going to be circular brackets. Okay, now let's check this. Awesome, so that is correct. Okay, so our intervals, so increasing was 3 to infinity, and decreasing was negative infinity to 0, union 0, 3. Okay, so those are going to be the intervals that we have. Now I've got another question for us. Okay, so it's saying, using your tables of signs from question 5, find all local minima and maxima for h of x. So the local minimum we said is going to be at x is equal to 3. Local minimum point is going to be 381, 3 comma negative 81, that's what we found here. The local maximum, we're going to say none, right? We don't actually know the point that is the maximum in this function. So I'm going to put in none, and I'll see if that's correct. Okay, so that's correct as well. Awesome. Okay, now we're on to the last 3 questions. Okay, now set up a table of signs. Okay, so they're asking us to now do the same question, now find the second derivative and do a table of signs. So if h of x, first derivative of h of x is 12x cubed minus 36x squared, second derivative, we just derive it once more. So 36x squared minus 72x. Now, for the second derivative, they're asking us to find the intervals where it's concave up, concave down. So, we obviously know here that, so essentially, I think it's if the second derivative is positive, is greater than 0, then it's concave up. If it's less than 0, it's concave down. And if it is 0, then it's a point of inflection. But then you, of course, have to check it in the original equation to make sure it is actually a point on the curve. So we already saw here that right? This is telling us it's concave upwards here because we're going down. Oh no, down and down. So we probably don't actually even have a point of inflection here. Okay, either way, let's put 3 because we changed the signs here, so that means that it's going to be a concave up. This is what I'm expecting, that it's a concave up here. So if we go ahead and plug 36x and then let's say 0, well, that's just going to be, okay, one's complete. So concave up. How do we find if it's concave up? Okay, I'm going to look through my notes. Okay, so basically, if the second derivative of a function is positive, as I said, it's going to be concave up. If it's negative, it's going to be concave down. And then if it's 0, then it's a possible point of inflection, as I mentioned before, if that point is actually defined on the curve. So 36x, and then let's say we choose 192 squared minus 72 times 192. Okay, so that's definitely concave up. So from 0, so concave up. Because if we put in 0, then it's just going to be 0. So it's going to be a point of inflection. So we're going to do, for our concave up, the interval is going to be 0, comma, infinity. 0, comma, and then let's see here if we can. So 0, comma, infinity is going to definitely be our concave up. 0, comma, infinity. That's going to be our concave up here. And then concave down, it's again going to be, it's just going to be the negative infinity that we were talking about before, right? So negative infinity, comma, 0, right? Because if we put in 0, then all we're going to get is, actually here, concave up. Wait a second, what if we substitute x is equal to 3? Oops, wait, I think this was an issue. 108. So we have positivity there. If we substitute x is equal to 1, we're negative. Okay, so we essentially want to find, okay, so we can just solve this here to see the points of inflection to then identify what our intervals are going to be. So instantly it's x is equal to 0. Divide both sides by 36x, we get x minus 2, x is equal to 2. So these are going to be the two important points that we're going to be looking at. So, okay, so anything less than 0, that's positive. Okay, so what we're going to be seeing then is negative infinity. Okay, so negative infinity. Sorry, let me just. Okay, negative infinity all the way to 0 is going to be concave up. And then we have, then let's plug in something like 1. Then that's going to be negative. Okay, so now we have concave down, which is very simply just going to be from 0 up until 2, I believe, right? If we plug in 2 here, okay, that gives us 0, so it's still, okay, so not including 2. So concave down is going to be from 0 to 2, and concave up, now let's put in 3. What's going to happen here? It's positive. So that means that our interval for concave up is going to be negative infinity to 0. So it would have been something like that. Exactly like how I've drawn it here. And then concave down, and then concave up is again going to be from 2 to infinity. Okay, so let's check if that is correct. Awesome, that is correct. So between 0, right, between x is equal to 0 and 2, we have concave down. So it's probably here, right? Because, yeah, so this is the point of inflection where it then starts to become, okay, that actually makes more sense. So up until here, the gradient to the curve, the gradient of the tangent to the curve kept on decreasing, and so it was concave down. At this point here, which is x is equal to 2, it then started to become more positive. So here it was really negative, the gradient, then it starts to become more positive. And so that is the point of inflection where it starts to become a concave up, and that's this here too. So that was our interval. So concave up is 2, well, I'll write it actually correctly. So negative infinity to 0, union 2 to infinity. So that's concave up. And then concave down is very simply just 0, 2. Okay, so that's basically it for this video. If you found it helpful, that's very good. Take a look at some of the other content on my channel that might interest you, and I hope you have a good day. Bye-bye.